Welcome back. So today we're going to prove the cone theorem. So let's just remind ourselves of the theorem. It has a lot of parts, so I'm going to leave it vertical for now. Okay, so let x comma delta be a projective KLT pair with delta boundary as before. Okay, then one, there are countably many rational curves. Ci on x such that well, with the following bound on their intersection with kx plus delta, and such that the cone of curves breaks up as the subset where kx plus delta is non-negative, plus this countable sum of rays spanned by the Ci. Okay, and then two guarantees for us essentially that this countable sum can't really accumulate. And the way we do that is by showing that for any epsilon greater than 0 and h an ample divisor, then if we look at the kx plus delta plus epsilon h non-negative portion instead, then we just get a finite sum. So I drew this picture a while back that basically this cone looks like, well, on the kx plus delta positive side, it could be wild, it could be round. On the negative side, it's this kind of rational polyhedral, but it's not a finite polyhedron, but it's locally finite in the sense that as soon as you wiggle around kx plus delta by some ample, then the negative side becomes finite polyhedral. And then 3, the existence of extremal contractions. So for f in any bar of x, an extremal face, but not just any extremal face. We want a kx plus delta negative extremal face. Then there exists an extremal contraction. And there exists a unique extremal contraction phi f from x to z, which is a projective morphism. Satisfying the properties 1, the push forward of OX is OZ, and 2, for any curve, phi f of c is contracted to a point if and only if this curve has class in our face. And then finally 4, that line bundles pull back as you might expect by this extremal contraction. So if L is a line bundle on X, such that LC is 0 for any C in our face, then L is phi f upper star of Z of LZ for some line bundle on Z. Okay, so if we have a line bundle that looks like it pulls back and that it is 0 on all the curves contracted by phi, then it really is pulled back. Okay, so that's the statement of the cone theorem, and that's what we're aiming to prove today. With two caveats, I guess. So I'm not going to prove the fact that these countably many curves are actually rational curves or can be taken to be rational curves, because of course, if you think about the case of P2, say, then there's just one ray. Sure, it's spanned by a line, but there are also higher genus curves on that line. They're just multiples of the hyperplane. So we're not going to prove that these rays can actually be spanned by rational curves, and we're not going to prove this bound on the intersection. These two things are actually very closely related, and the reason is that essentially they come from the bend and break method, which I decided to skip to save time to get more into the singularity stuff. So if you're interested in these two pieces, we'll also just say read the section on bend and break, which is in the first chapter of Kolar-Mori. So first, for simplicity, let's just abbreviate kx plus delta as just k. And then we have an A such that A kx plus delta is Cartier. And then by the rationality theorem, we saw that anytime we have these Neff thresholds in the rationality theorem, the denominators are bounded by some number depending on A. So specifically, recall that the denominators in the rationality theorem are bounded by A times dim x plus 1. And the point is that this number is independent of the particular divisors we plugged into the rationality theorem. And so because we have this upper bound on the denominators, there's some uniform common denominator that works in the rationality theorem for any divisor you could possibly plug into it. So we'll just denote that M. Just choose some common denominator. Okay, so that's the other piece of notation, this M. And then let me draw this picture that explains the idea of the proof that I think I drew at the beginning of the class as well. So we have our cone. So let's say inside of, we're inside of N1, we have the hyperplane k equals 0. And then we have our cone, which a priori is complicated on both sides. We're going to prove that it's not, but okay, here's some picture of it. And then we're going to take some ample, and our ample class is going to be over here. So that's our hyperplane h equals 0. And so our cone of curves is all inside of the half space h greater than 0, because h is ample. And so k might not be Neff. Okay, if k is Neff, then there's nothing to prove. The whole statement is vacuous. So let's assume k is not Neff. So we have this picture where k equals 0 slices in the middle of the cone. Then what we can do is apply the rationality theorem, and we can just start taking h plus tk for t greater than 0, and now we're going to get closer and closer to our cone of curves, and eventually we're going to hit the cone of curves. We're going to hit the Neff threshold, and we're going to hit somewhere that's exactly on this cone. And so h plus rk will be some Neff divisor. It'll also be rational. So we started with h, an actual Cartier ample divisor. K is a Q Cartier divisor. R is some rational numbers. So we'll get this Q Cartier Neff divisor that's exactly on the boundary. And now what we're going to do is we're going to show that, well, whatever the intersection of this hyperplane h plus rk equals 0 with our negative piece of the cone of curves is, we're going to show that we can cut it down further to make it smaller dimensional. Basically, we're going to perturb our h plus rk equals 0 by some other ample divisor. So we're going to perturb this so that before we had this face cut out by h plus rk equals 0. And now when we perturb it, we get a face that's strictly smaller dimensional. And then continuing this way, we get all these rays on our cone that kind of span every possible face on the negative piece. But because they're all given to us by the rationality theorem, they all have rational slope, and there's only countably many of them. And so that'll essentially will lead us to the proof of the cone theorem. So really the key input is this rationality theorem that by the rationality theorem, we can cut out these faces on the negative piece of our cone by some actual Q divisors using this process. Okay, so that's the rough idea. And if you've seen the bend and break method before, which is how you can prove this in the smooth case and with no boundary, then you should think of this as a little analogous, because in the bend and break method, what you do is you say you take some curve that's k negative, and then you deform that curve until it breaks up into smaller curves, and that tells you that whatever your curve was is the sum of curve classes of lower genus, and eventually you break them down into genus 0 curves, and you get that all your k negative curves are sums of genus 0 curves, and those give you your rational curves that span this part of the cone of curves. And you should think of this perturbation argument as analogous to this breaking up your curve argument, but that works in the singular case, where kind of we have this face that maybe has non-rational curves on it and isn't minimal. It really is a sum of other things in the cone, but by this perturbation, we break that up into a sum of its rays that span it. You can think of that kind of analogous to breaking up your curve in bend and break. Okay, so let's actually write down the proof. So let's suppose that, like I said already, suppose that k is not Neff, because if it is Neff, then the whole statement is vacuous. So step 1, if L is any Neff divisor, but not ample, then we can define the face cut out by L to be the half space L equals 0. Sorry, not the half space, hyperplane L equals 0, which we can write as L perp intersect the cone of curves. So that's exactly what's going on here. That'll be, in this case, this face over here, if L is h plus rk. But for any L that's Neff but not ample, we get such a face, and the point is, because we're assuming that L is not ample, this is not just 0. So if we happen to pick an ample, then this intersection would just be 0. Okay, so let's also suppose that this is on the negative side. So maybe slightly weaker, suppose that FL is not contained in the positive side. So it might be one of these faces like in this picture, but it might also be a face like over here that that intersect k equals 0, but it's just not contained in the non-negative side. Okay, and now we're going to apply the rationality theorem with some other ample and this nef. So let's define RL and H to be the supremum or the max over T and R, such that if we take NL, which is some nef divisor, plus H, well now NL plus H is big in nef because it's ample plus nef. Plus in our rationality theorem, we have T times K nef. So we take the threshold for this RL, but let's divide in this T, let's divide by our common denominator M. So now T is actually an integer, is the point. So this RL, we've normalized everything. So this is really an integer because we know we have this common denominator M in our rationality theorem that works for any divisors that we can plug in. Okay, and now we can think of what happens when we increase n. So as we increase n, the point is that RL n comma h is less than or equal to RL n plus 1 comma h, because L itself is nef. So if we add more copies of L, we're not making any new curves negative. We might be making new curves non-negative because maybe there's some more positivity we're adding, but we're not making anything more negative by adding L. So this threshold just gets bigger as we raise n. But on the other hand, if we just pick some class in this face corresponding to L, so that's some pseudo-effective class where L is 0. So if we look at NL plus H plus T over M K times this times this psi, this intersection is independent of n because L dot psi is 0. So this is, well, what do I want to say? So I guess we want to go up to this threshold RL n comma H. All right. So the point is that this divisor is nef. Sorry about that. So this is nef because we're at the threshold. So whatever this is greater than or equal to 0 because psi is a pseudo-effective class. L times psi is 0. H times psi is strictly positive. So we can divide. Right. So since H times psi is strictly positive, then K times psi has to be strictly negative. No, that's not what I want. Right. We want to pick our psi. So here's where we use this assumption that FL is not contained in the K positive cone. So we can pick some psi that's in FL and in the negative part. Sorry about that. So pick some psi that's in this face and that's away from the NE positive part. Okay, great. So now we know that H times psi is greater than 0. We know that K times psi is strictly less than 0. We know that L times psi is equal to 0. And so we can rearrange and divide and we'll get that RL and H is less than or equal to M times H times psi over K times psi. Okay, so that was the point. And the point is that this is uniform. it's independent of n, it's independent of L, and so we have these integers that have this independent upper bound, and they're increasing, so eventually they're going to stabilize. To some number, we'll just call RL of H for n greater than or equal to n naught. Okay, so that was the important point, is that eventually this Neff threshold stabilizes when we keep adding multiples of L. So what does this buy us? So now let's look at n strictly above this stabilization number. Then if we consider these divisors, dnlh, so let's clear the denominators, this m. So these are Cartier divisors. So we'll do m times nl plus mh plus this integral threshold RL times k. So it's just exactly these divisors here, but we've cleared the m in the denominator. So if we look at these divisors, then the point is that if we're above this threshold, then this being Neff, so of course it's Neff because we're at this RL, this implies that dn minus 1 LH is also Neff for the same R because we're above this stabilization number. So again, the point was that if we're for small r, then maybe we need more copies of L to become positive. But because of the stabilization, we reach a point where now we don't need those L's anymore to have this Neff property because we've stabilized. So once we're above this threshold, we know that dn LH being Neff implies that dn minus 1 LH is Neff because this R is the same. And so if we look at L restricted to the face where dn LH is 0, so this is the face cut out by this D, then this is also 0. Because we're at this point where if we decrease by L, we still stay Neff. So if we have some curve where D is 0 and we subtract off a copy of L, well, L better be 0 on that curve as well if we're going to stay Neff. So this implies that this face corresponding to this D is actually a subset of the face corresponding to L, which we said was non-zero, and the claim is that this is also non-zero because D is not ample. And the reason D is not ample is because we can take one of these xi's where like up here, where H is positive and K is negative. Okay, so what we've said is that given an L, we can start adding multiples of H to get this possibly smaller face corresponding to this divisor dnLH. Right. So now we have this face, and now we also want to know that, like in our picture, if we picked FL to be, say, this face over here, where one of the boundary rays of that face is actually on the k equals 0 point, we want to know that this FD, so if this is FL, we want to know that this FD is over here in the strictly negative part, not in the 0 part. So or equivalently, we want to know that this minus 0 is contained in the strictly k negative part. And the reason we know that is because L is 0 on all of this face FD. And so if we just look at the expression, well, L is 0 on this face, H is strictly positive on this face because it's effective, so K has to be strictly negative on this face. So L restricted to FD minus 0 is strictly positive, so K restricted to FD minus 0 is strictly negative. Okay, so in this way, we found a procedure that says if you start with any L, with any Neff line bundle L, and you look at its face and you assume its face is on the non-positive half, then by adding some multiples of an ample, we can cut down the face to a face that's strictly contained in the K negative part. But now the issue is it's possible that this FD is the same as this FL. So we need to argue that we can actually cut down the dimension, that we can pick our H such that this FD is a strict subset of FL, and in this way we can cut down our faces down to rays. So that's step 2. So suppose that the dimension of FL is strictly bigger than 1, then the claim we can pick H such that this new face FD and LH has strictly smaller dimension. And this was exactly what we said in our strategy up here, where we started with this red face and now we want to perturb to this blue one that has a strictly smaller intersection. Okay. So pick some ample basis, which we can do for the full Néron-Severi. Well, it has size, the Picard rank, by definition. And now let's look at these divisors. So let's say we've gone up to the stabilization point or past it for each of the finitely many H's. Then when we look at these as functions on FL, well, on FL, L is 0, so these as functions are just the same as the restrictions of MHI plus RL of HI K restricted to this face. And whatever they are, they give us some functions that are in the dual of the span of FL. So we have this face, it spans some subspace, some linear subspace, and whatever these functions are, there's some functions in the dual. But the point is that the HI are linearly independent. So if the span of FL dual is not, or maybe just the span of FL, if the span of FL has dimension greater than 1, then these D's as functions can't all be 0. Because we've picked this basis HI, but this expression is telling us that when we restrict to FL, all of them are proportional to K. And so if our span of FL is greater than 1-dimensional, that just can't be the case. They can't all be proportional to K because they're linearly independent on the large space. So as long as the span of FL has dimension strictly bigger than 1, then we can find some D So if some I, where this restriction is not identically 0. And now that works, because if this is not identically 0 on FL, then the face it cuts out, where it is 0, has to be strictly smaller than FL. Sorry. Is a strict subset of FL. And so we found some ample so that this this process cuts out a strictly smaller face. And so now we can just keep repeating. Then we get these. We get that each one of these faces FL is spanned by some one-dimensional rays, because we just keep applying this as long as our FDs are bigger than one-dimensional. And they're still of the form face associated to a Neff divisor because of the construction. D is some Neff divisor. So basically we cut down to these rays of the form FL, where L is Neff. The dimension of FL is one-dimensional, and FL minus 0 is contained in the strictly negative part. That was our property for FD. So even if FL intersected the K0 part, we did this perturbation so that FD was in the strictly negative part. And the point is that not only do we have all these rays, we also have that each face FL prime for L prime Neff with FL prime not contained in the positive part contains one of these rays. Okay, so now we want to show that these rays, these FLs for that are one-dimensional and that are in this strictly negative part, we want to show that they give us these countably many rays that span our cone of curves. And the point is they're countable because all of our divisors that we define here are Cartier. Okay, so. So step 3 is to say that essentially we have our conclusion up to taking a closure, because we have these countably many rays. So if we just take our linear combination a priori, this locus isn't actually closed a priori because we have this countable sum. So step 3 is to show that at least up to taking a closure, then this is all of any bar of X. And just to simplify the argument, let's call this thing W. Okay, so how do we show this? Well, let's just suppose not. So first of all, it's clear. One direction's clear. So this is contained here just because we have the closure of some span of pseudo-effective classes. So let's suppose that this W was a strict subset of any bar of X. So I'm going to draw some picture. So we have whatever any bar, and then here's k equals 0, and then we have this W, and if there's a strict inclusion, then W will have to be, spanned by some rays over here, and it's some closure like this, and so we have this room between W and any bar, and because they're both closed, because W is a closed subset inside of any bar. If they're not the same, then we can find some hyperplane, some rational hyperplane, say M equals 0, that separates them. So where all of W is contained in the M greater than 0 part. Where all of W is contained in the M greater than 0 part, but the M less than 0 part of any bar is non-empty. So we can kind of separate them by this M. Okay, so we pick such an M. And now we apply the rationality theorem again to kind of perturb this M so that we cut out a face on by some divisor of the form, H plus multiple of K, so that we're on the boundary of any bar, but avoiding W. So the point is, because W is in the M strictly greater than 0 piece, we're going to kind of perturb this M so that we end up like over here. And now we cut out some face of any bar, but we're just completely away from the purple piece. But now we apply our argument again from the previous step. And so by the previous step, anytime we have such a face that's cut out by an F divisor, we can find a smaller ray that's cut out by it. But that ray is by definition inside of W, because W is exactly the closure of the span where you have all of these rays cut out by F divisors. So that's a contradiction. So by the previous step, we can cut out a face. So we can cut out a ray. Of the form FL, but not contained in W, and that's a contradiction just from the definition of W. Okay. So that tells us that W really is the whole cone, and now what we need to show is that we don't actually need to take a closure, that everything's actually already closed. And to do that, we'll actually show. Never mind. Okay, so we're just going to show that everything's already closed. Okay. Any questions up to here? Okay. So now we're going to show that there are no. So step 4 is the claim that there are no accumulation points of these FLs. So basically, these FLs don't accumulate inside the region k strictly less than 0. So in this half space. So you can think of you have all these countably many rays that are spanned out by rational Neff divisors, and the closure of their span gives us the full effective cone, while the closure of their span with the non-negative part gives us the effective cone. And we're going to show that they can't accumulate inside of this strictly negative subspace. These rays, they can accumulate at k equals 0, but we don't care about k equals 0. And essentially that'll show that this has to be closed already. Because like on the it's already, by definition, it's already closed inside of the half space k greater than or equal to 0, because we're just taking that closed cone on that half space. And so if you can't accumulate on the opposite side, then there, you don't need to close, you don't need to take a closure, because everything's already in the linear span. Okay. So let's take our L's. They're one-dimensional arrays, so let's write them as the spans of some curved classes psi L. And now let's pick some ample basis, just like before. But now we'll pick a slightly different basis. So we'll pick amples HI such that they form a basis with K. So we'll just extend K to a basis. And now we wrote down this computation that HI dot our array, or dot, let's say, our generator for our array, and let's say this is an integral generator. That's pretty important. These are rational arrays, so they have some integral generators. So now we can look at this HI psi L divided by k psi L, and this is going to be some integer with denominator m. Again, because of our rationality bound here. Where did we do this computation? Right here, this computation, except now we're all the way up to the threshold where things don't change anymore. So it's actually an equality, because this is actually a curve where d is 0. So right, so we have this expression where hi psi over k psi is an integer over a uniform denominator. And so the point is that these are a basis for the dual space, this k h1 through h rho minus 1. And so hitting a class with these bases gives you coordinates on our space. So psi maps to the tuple k psi h1 psi h rho minus 1 psi gives coordinates for n lower 1. And now once you have these coordinates, now these ratios should look familiar to you, because they're ratios of the form all our coordinates divided by the first coordinate. These ratios are exactly projective coordinates, sorry, affine coordinates for the projectivization. So if we look at the projectivization of n1 of x, and we look at the open affine subset, and this is all happening over the real numbers, by the way. I think these are just Euclidean spaces. So we look at the open affine subset defined by k not equal to 0. Then these ratios give us coordinates for this open affine. But now we care about this half space k strictly less than 0. Over the real numbers, when we're projectivizing, k strictly less than 0 and k strictly greater than 0 are the same thing. When we're projectivizing, it's just not equal to 0. So this whole subspace maps to this A. This affine space should be a rho minus 1. So the space Let me give some notation. What notation did I use? Right. So let's call the space, the half space k less than 0. Let's call it U. So then we have this, under the projectivization map, we have this map like this. That's basically the quotient by r greater than 0. And so all of our FLs over here, because we're projectivizing our rays, every point on the ray goes to the same point because we're projectivizing and they're all on a line. And what does this expression tell us? It tells us that the rays in U, the rays that are contained in the strictly k less than 0 piece, they map to something with coordinates of the form integer divided by m under this projection. So let me call this star equation. And let's call this map, I don't know, G. So we have all these rays, and when we map them down to the projectivization, where they all land inside of this fixed affine chart that's just the Euclidean space, and they all go into this integer lattice. It's not the usual integer lattice, they have a denominator, but the denominator is fixed. And so they can't accumulate. That exactly tells you that the rays don't accumulate, because when we project them down, when we quotient out by the ray direction, they just become some discrete set. Okay, so that proves the claim, and it again reduces to this rationality theorem that gives us this uniformly bounded denominator. Okay. So, or maybe I'll say, so then the classes of FL in the projective space can't accumulate inside of this A rho minus 1. And that tells us that the rays can't accumulate inside of U. Okay, so we have these rays, they're kind of discrete inside of the strictly negative half space. Now we want to justify this piece where when we perturb by an ample, then we get only finitely many rays. But now the point is that when we perturb by an ample, if we look at k plus epsilon h less than or equal to 0, and we take the projectivization of this stuff, then this is actually, sorry, I should write here the cone, like the intersection with NE. So if we look at the locus of NE, where k plus epsilon h is less than or equal to 0 for h ample, then this is some compact subset. And so we have this compact subset. We look at it's inside this projectivization of this U, and so these FLs are all integral points inside of this U. There are these discrete points in P of U, which is just this affine space. And when we intersect them with this compact subset, we have to get finitely many. So finitely many classes of FL, so finitely many classes in this projectivization of these lines lie inside this compact subset. K is not a good, let's call it V. Lie inside V. So finitely many rays of the form FL. Lie inside this half space K plus epsilon H less than or equal to 0, and so in particular, finitely many lie inside of the half space where they're strictly less than 0. Okay. So that gives us the statement that, well, that gives us that there are only finitely many of these, but now we actually want to show that these finitely many span all of any bar when we add the positive part. So, so we know that any bar K plus epsilon H greater than or equal to 0 plus this now finite sum so now we have this finite sum. Whatever this is, it's contained in the effective cone, but it also contains kind of the sum over all of these one-dimensional arrays. Because either your array where when you perturb by epsilon h, you're still in the negative piece and then you appear in the sum, or you're not and then you appear in the K plus epsilon h greater than or equal to 0 piece. So we have these containments, but this is a finite sum in the middle. So it's already closed. So this is closed. We also know that when we take the closure here, we get W. Let me use a different color. So we know the closure is W. So because the middle is already closed, we know that it's contained inside of this middle piece. But we also know that this W actually just equals all of any bar of X. That's what we proved in the previous step. So all this has to be an equality. And so this was part 2 of the theorem that when we perturb by some ample, we get the non-negative part plus a finite sum of rays is the whole effective cone. Okay, so then step 5, I'll just summarize. Now we'll use a limiting argument to show that when we don't perturb by an epsilon, so basically our limit as epsilon goes to 0, to show that when you don't perturb by epsilon, the cone is already closed. So basically, like the idea is that if we look at the K plus epsilon H less than or equal to 0 part, that's some closed cone, but it's spanned by finitely many of these rays. And then, well, it's spanned by the 0 part plus finitely many rays. But then as we limit, we kind of pick up more and more of these FLs as we take the limit as epsilon goes to 0, but we always get kind of finitely many, but more and more. And then you use that, you kind of write everything in this cone. Like you write everything in the limit of this cone as a limit of guys in one of these finite cutoffs for a fixed epsilon, and then but let epsilon limit to 0, and then you get that everything's already closed basically. Okay, so I'm not going to write down the details of that argument. It's more kind of convex geometry, but it should be believable from this point. Okay, so that proves parts 1 and 2 of the cone theorem, except that we don't actually know that these FLs are spanned by actual curves. So far, we just know that there are some rays spanned by curve classes, and they're of the form perpendicular to an F divisor intersect our cone. So to prove that these are actually spanned by effective curve classes rather than just limits of effectives, we actually need to prove kind of the next part, which is essentially using the base point free theorem that we have contractions. So to do that, we also want to know more generally, because we want to have extremal contractions not just for rays but for any faces. So step 6 is the claim that if F is any k negative extremal face, then F is the face associated to some F divisor D. So we already know that's the case for the specific rays that appear in this decomposition in the cone theorem, but we want to show that all of them are faces associated to F divisors. So for D, F, and Cartier. Okay, so to do that, let's take V to be the vector space, the span of our face, and then perpendicular. So these are all the divisors that are 0 on the span of our face. And so from this decomposition, we know that these faces F that are on the negative side have to be rational because they have to be spanned by these FLs. So that implies that this V is a rational subspace. Meaning that it's has a basis of with rational coordinates. Okay, so now let's pick some small epsilon. Pick some small enough epsilon so that this particular face is still on the negative piece of our epsilon ample perturbation. And now, so let's draw a picture. So we have our face F. Here's k equals 0. Here's our non-negative part. Let me use a different color for F. So there's F. And now look at all of the rays that span the negative side. Look at all of them that are not contained inside of F. And take the cone spanned by just all of this stuff. So here it is. Let's call it W. So W is the sum of any bar where k plus epsilon h is greater than or equal to 0, plus the sum of those rays which are not contained in F. So I guess I should draw, here's our perturbation. We pick a perturbation that's far away from F because we can make epsilon as small as we want. So here's our K plus epsilon H. Okay, so we look at this W, that's a sum of all of the rays on this negative piece that aren't contained in F. And now that tells us that we can find some G that sits in between, that separates the face F and the closed subset W. So we can pick some G over here. Actually, sorry, I want to pick some G that vanishes on F, but is strictly positive on W. So here's our G equals 0. So saying that G is 0 on F is like saying that G is contained in V, but we want to, because we can separate F and W, they're separated by some open set. Then the point is that we can pick this G such that G is strictly greater than 0 on W. So that's what we want to pick. We want to pick a G that's strictly greater than 0 on W, and then that vanishes on F. And now this G would be a RNF divisor if G was actually the class of a divisor. But now the point is that, a priori G is just some element of this vector space V. But the point is that this condition, this is an open condition in V. And so since V is rational, the existence of one such G implies the existence, of this open setsworth, and because V is rational, then inside of this open setsworth we'll have some rational, some points with rational coordinates. But now once we have this rational guy, then we can scale clear denominators and get that it's the class of 1 over MD for some actual divisor D. So D restricted to F is 0. D restricted to W is strictly greater than 0. And so because W and F together span the whole cone, just by definition, because we took W to be the span of everything except for F, so together they span everything, then D is Nef, and D equals 0 if and only if, or maybe I'll write it as D perp intersect NE bar is exactly our face F. Okay, so we found a D that cuts out any of our negative extremal faces. And this D is some Nef Cartier divisor, and now we can apply the base point free theorem to this D. So step 7, we have our extremal face F. Now we look at MD minus KX plus delta. So this was K before, but now just to get it back to the notation of the base point free theorem. So this is greater than or equal to 0 everywhere, but it's also equal to 0 on F. This Kx plus delta, well, somewhere it's less than or equal to 0, somewhere it's greater than or equal to 0, but the point is that Kx plus delta is strictly less than 0 on F, because F is some K negative extremal face. And so that tells us that for large M, and I should say this is D is not just 0 on F, but it's 0 on F and strictly greater than 0 everywhere else. And so for large M, this difference is actually ample. Because if you're on F, we have 0 minus something negative, something strictly negative, so we're positive. And if you're away from F, we have something positive minus something fixed. So as long as we make M very large, then we get it strictly positive. So this difference is ample, and D is an F by construction. So we can apply the base point free theorem. We get that, we'll just say for B large enough, this linear series is a morphism. Okay, so then in the limit as B goes to, so let's take the limit as B goes to infinity and let Stein factorize. Then some theory about base point free linear series tells us that this, so this stuff about Itaka fibrations that we didn't cover in this class tells us that eventually this stabilizes, that the Stein factorization of these phis for large enough B are all the same. So let's call it phi F. So because we Stein factorized, Z is normal, but everything's still projective. So this is a projective morphism with phi F Laura star OX equaling OZ. Again, this comes from this theory of Itaka fibrations that when we Stein factorize, we always get it factoring through something that satisfies phi F lower star OX equals OZ, and for large enough B, kind of you don't have this finite piece. Or I should say, I guess maybe even if you do, it doesn't matter because just factor through just take Z to be the part where phi lower star OX is OZ, and then the point is that for large enough B, this is independent of B. Okay, so we have this linear series that gives us this morphism, and now because it's some semi-ample linear series, we know that phi F of C equals 0 if and only if C dot D equals 0 by semi-ampleness. And so, but C dot D equals 0 if and only if the class of C is in this face. So we get that phi F satisfies the second property of extremal contraction, that something's contracted if and only if the class is in the face. And now the observation is that these two properties, so phi F is as in part 3, or maybe I called it part C of the theorem. But now the point is that these two properties uniquely determine phi F, because on the one hand, topologically, like if you just think about the underlying point set of the variety, then the condition that a curve is contracted if and only if your you're in this face, that determines phi topologically. That just tells you that phi topologically is just the quotient by the equivalence relation that any 2 points that lie on a curve inside of the space are identified. But then the condition from the Stein factorization that the push forward of OX is OZ, that determines Z as a scheme. Because once I have the topological space, then I just endow it with the structure sheaf, the push forward of OX. And so that uniquely determines phi as a morphism from these two conditions. Okay, so we're almost done, but maybe it's better to stop here for today than to stop in the middle of a step. So what's left is now that we have our unique extremal contraction, then this tells us that there are rational curves, because if either if phi doesn't contract in any curves, then it has to be the identity because it has connected fibers, so it can't be finite. And so if phi is not the identity, if f is not is a non-zero face, then it has to contract some curves. Whatever those curves are, they're on F. So that tells us that F is actually spanned by the classes of actual curves. And then we need to show that line bundles are pulled back. Or the line bundles that are zero are pulled back.